Lecture number 2, Rankine cycle, and today we'll be solving some example in a Rankine cycle. Example 2.1, example 2.1 of power plant technologies by Wakil. Consider three Rankine cycle, all exhausting to 1 psi. Cycle A operates at 2500 psi and 1000 degree Fahrenheit. Cycle B operates at 2500 psi saturated steam, and cycle C operate with the superheated steam at a temperature equal to that of cycle B but with a pressure of 1000 psi. Calculate the efficiency and exhaust steam quality of the three cycle. So we will be only solving cycle A in this lecture. Cycle B and cycle C, you can find the data of the answer of cycle B and cycle C in your book. Now, to solve the example, to solve this question, first we need to consider what are the given parameters or what are the given data in this example. So it's say like all exhausting the Rankine cycle, which is exhausting at 1 psi. So exhausting mean like the exit pressure at which the turbine is exiting. That mean like the condenser pressure, inlet of the condenser and exit of the turbine. So that is 1 psi. Um, then you say like cycle A operates at 2500 psi. So operation pressure mean like the inlet pressure of the turbine. So these are the exhausting pressure, which is actually the condenser pressure, and the operating pressure, which is the inlet of the turbine pressure or the boiler pressure. Now the boiler pressure is 2500 psi and 1000 degree Fahrenheit. So what we have to do, like we have to look at the steam table, and in a steam table, first thing first, we have to check whether this 2500 psi and 1000 degree Fahrenheit is in a saturated region or in a superheated region. So let's check the steam table. So in a steam table of Wakil, let's say, so we have got pressure table over here. And the pressure table, if I'm looking at the pressure table and a value of 2500 psi, the temperature given is equal to 668.11 degree Fahrenheit. So that means like the steam at 1000 psi, 1000 degree centigrade, and 1000 degree Fahrenheit and 2500 psi is superheated. So now we have to go to the superheated steam table and find the enthalpy and entropy of superheated steam. So for a pressure of 2500 psi and a temperature of 1000 degree Fahrenheit, let's check the value of enthalpy and entropy. So 2500 psi, so you can just check like the saturation temperature is 668.11 degree Fahrenheit, and let's check the at the temperature of 1000 degree Fahrenheit. So that's the temperature at 1000. That's the value of enthalpy and entropy at 1000 degree Fahrenheit. Let's check it back. So that's it. So we have got the enthalpy, which is 1457.5, and we have got the entropy, which is 1.5269. Coming back to the question, so that means like enthalpy would be 1457.5 BTU per pound mass, and the entropy is 1.5269 BTU per pound mass degree Rankine. Uh, as we there isn't anything given about the irreversibility in a turbine or irreversibility in a Rankine cycle, so we would assume like the turbine is working in reversible adiabatic process, or in other words, we would assume like it is expanding in an isentropic. So that means like S1 would be equal to S2. So from that one, S1 is equal to S2, and that also mean like if we want to compare it with the value of Sg at 1 psi, which is actually when it is expanding. So that means like the value would be either less than or greater than Sg. So in our case, let us check this one. So in this case, like the at 1 psi, the value of Sg is 1.9781, while our own value of which was S1 equal to S2, our own value was somewhere equal to 1.569 or something like this. So that means like our value is less than the value of Sg. So we are inside the vapor dome, also, or we are in a saturated region. Now coming back to the question. So that means like we are in a saturation region. So we will be using the formula. So that means like S, this is Sg is greater than S2. So back we have got the formula, which means like S2 would be equal to Sf plus X2 Sfg, and also for the value of H2, that would be equal to Sf plus, sorry, Hf plus X2 HFG. So we were interested in the value of enthalpy over here. But yes, in this question, we do not have got the value of X. So we can find the value of X from here. So using this at the pressure of 1 psi. So using these value of SF and SFG at 1 psi, just putting them value, and we can find the value of X, and that is equal to 0.7555. Make sure your X value or the dryness fraction is at least 3 decimal places, so that's a little bit more accurate towards your answer. Now, as we have got the value of X2 now, which is the exhaust steam quality, uh, we can find the value of H2, and then using the same formula which is over here, H2 is equal to HF plus X2 HFG, and we can find the value of H2. Now moving forward to state 3 over here. So that was a superheated cycle. From 1 to 2 we have got an expansion, and that was expansion inside the vapor dome. Then from 2 to 3 we have got the constant pressure heat removal in a condenser. So in a condenser, we normally assume like when we are exiting from the condenser, the steam should be converted to saturated liquid. So that means like at state 3, we are having a liquid which is saturated. So from the saturated table at 1 psi, we can find the value of enthalpy, which is also equal to over here, which we have already find out from here as well. So which is equal to 69.73 BTU per mass. Now moving forward to state number 4, which is when we are increasing the pressure in a pump. So from 3 to 4 is a pump work. And now there are two methods to find out these things. Either you have to, if you have got the compressed table, as we are now in a compressed region. So we have got S3 is equal to S4. Now obviously there will be the S4 is in a compressed region, so we do not need to know like whether it's a greater than or less than SF, so something like this. So just move to S4. Now you have got S4 and you have got a pressure at 4, and the pressure of at 4 is over here 2500 psi. So using this entropy and the pressure value, which is 2500 psi absolute, you can just go to the compressed table and find the value of enthalpy from that compressed table. But in a most of the time, the compressed table are either not that much I would say like expanded, it's a compact table, or sometimes it is difficult to find the value, or even sometimes the compressed table is not available. So you can use different method to find the value of 4 enthalpy H4 in here. So work done is equal to, normally work done of the pump is equal to VdP, and that means like if I'm looking at from 3 to 4, so that will be V3, and that would be change in a pressure V4 minus V3. So that's the value, that's the work done of the pump. That's also equal to, in terms of enthalpy, if you are talking about, that's also equal to H4 minus H3. So in this question, what we have got is, we have got the value of V3, which is Vf at 1 psi. We have got the value of P3, which is 1 psi. We have got the value of P4, which is 2500 psi. And yes, we have got the value of X3 from here. Sorry, H3 from here. So you can find the enthalpy H4 in this question. But make sure, like, when you are solving this question, the value at this, or the unit at this point, would be different than the unit at this point. Make sure you multiply with the in square divided by BTU, convert that, both of the unit, or convert this type, this side unit, so it can actually be equal to this side. Now we have already got all of them, all of the enthalpies. So you can find the work done of the turbine. You can find the work done of the pump, which is already there. Somewhere we did find the work done of the pump, H4 minus H3 anyway, if you can find it. Work done of the, and then you can find the network. Network divided by the heat supply would be the efficiency of the Rankine cycle, and which come up as 43.29. Now moving forward to another question, and that is example 8.3 and example 8.3 of Moran and Shapiro. That's in the reference book anyway. And then the question is about the evaluating the performance of the ideal reheat cycle. Steam is the working fluid in an ideal Rankine cycle with a superheat and reheat. Steam entered the first stage of the turbine at 8 megapascal, 480 degrees centigrade, and expand to 0.7 megapascal. It is then reheated to 440 degrees centigrade before entering the second stage of the turbine, where it is expanded to the condenser pressure of 0.008 megapascal. The net power output is 100 megawatt, determining the thermal efficiency, the mass flow rate of the steam in kilogram per hour, and the rate of heat transfer out from the condenser steam as it passes through the condenser in megawatt. It's like discuss the effect of the vapor power cycle. We can only discuss the effect of vapor power cycle if we are having the values of example 8.1 or example 8.2. Yes, we can check it later on anyway. So it means like we have got two stage of the turbine, uh, and if the pressure of the two stages is already given. So in the first stage, when we are expanding in the first stage of the turbine from state 1 to 2, the inlet pressure is 8 megapascal and the temperature is 480 degrees centigrade. When it is expanding in the first stage of the turbine, the pressure dropped to 0.7 megapascal, and obviously we do not know about the quality, so we will retain that thing and then we will discuss it later on. Then from 7 at a constant pressure, it is reheated and it is reheated to a temperature of 440 degrees centigrade. Then it is expanded from that pressure and that temperature is expanded to a condenser pressure and condenser pressure of 0.008 megapascal, or we call it as a 8 kilopascal. It is then condensed to a saturated liquid, and then it is pumped to a pressure which is equal to the boiler pressure of 8 megapascal. So if we start solving this question, we have to look at the steam table, and that steam table would be like, we will first check the steam table of a saturated steam table. So in a saturated steam table, let's find the first thing first. Let's find the at 8 megapascal and 480 degrees centigrade. Let's check it whether it's lying in a superheated condition or saturated region. So moving to a saturated vapor, liquid vapor pressure table, finding the pressure of 8 megapascal, which is 80 bar. The unit over here is in bar. So 80 bar, so the temperature, saturation temperature is 295.1, which is obviously at 8 megapascal, 480 degrees centigrade, our steam would be in a superheated region. Uh, Also, if you can just check like for 0.7 megapascal, so for 0.7 megapascal, the temperature is given as 440 degrees centigrade. So in here, which is 7 bar or 0.7 megapascal, the saturation temperature is 165. So again, like 0.7 megapascal and 440 degrees centigrade is in a superheated region. Similarly, if we will come back to 0.7 megapascal steam table to check like whether the it is dropping or expanding inside the vapor dome or outside the vapor dome. So first thing that was like we have got at superheated condition. So we will go to a superheated steam table and find the enthalpy H1 and entropy S1 from the superheated steam table. So in a superheated steam table at a pressure of 8 megapascal or 80 bar and a temperature of 480 degrees centigrade, the enthalpy is 3348.4 and the entropy is 6.586. So that's the value of entropy now. So now going back to the question, so at state one, we have got both the enthalpy and entropy known now. Now, what we have to do, like in an isentropic expansion, if it is ideal and ideal super reheat cycle, so S1 is equal to S2. And obviously, again, we have to check this, the value of S2 with the value of Sg at 0.7 megapascal. If the value of Sg is greater than the value of S2, then that means like we are inside the vapor dome. And if it is inside the vapor dome, then that means like S2 would be equal to SF plus X2 SFG. And similarly, H2 would be equal to HF plus X2 HFG over here. So let's check the value of Sg at 0.7 megapascal. So at 0.7 megapascal, we have got the entropy of saturated vapor. So entropy of saturated vapor is 6.7080, while in our case at a superheat, it was equal to somewhere 6.6. So obviously the Sg value of Sg at 0.7 is greater than the S2 value. So that means like we are inside the vapor dome. So coming back to the question, that means like we can find the value of S2 from this formula or the formula we have already discussed over here. So we can find the value of X2 from this formula, the value of from the uh, entropy value. Putting X2 in this formula, H2 would be equal to HF plus HFG, and we can find the value of enthalpy, and that is enthalpy at state 2. Now going back to the same thing now, say going back to state number 3, which is 0.7 megapascal and 440 degrees centigrade. So we have already checked like at 0.7 megapascal, the saturation temperature was 195 something. Sorry, 165 something. So that means like 440 degrees centigrade is in a superheated region. So going to the superheated steam table at 0.7 and 440 degrees centigrade, we can find the enthalpy value as 3353 and the entropy value as 7.757571. Now, from the second stage of the turbine, it is expanded to the condenser pressure, which is 0.008. Now, the same case would be the S4 would be equal to S3. Finding like whether it's inside the vapor dome and outside the vapor dome, you have to compare again with the value of Sg at 0.008 megapascal. Uh, Once you find out like it is inside the vapor dome, you can find the value of x2. And once you find the value of x2 from the entropy formula, you can put that value in the enthalpy formula and find the enthalpy at state number 4, which come up as 2428.5. Um, then obviously the other values are quite similar, so you can find the value of state 5 as HF value at 0.008 megapascal, and using the same pump work for the state number 6. But do not need to worry about like the units now, as work done in a pump would be equal to V5 P6 minus P5, and that would be equal to H6 minus H5. So the unit at this side of the equation would be equal to unit at this side of the equation. So you do not need to worry about the unit conversion. Once you find all the enthalpies, then you can find the net power, the efficiency, thermal efficiency. So finding the net power would be turbine work from state 1 to 2, in this case state 1 to 2, plus the turbine work from state 3 to 4, minus the pump work from here, divided by the heat transfer, which is actually from state 1 to 6 to 1 in a boiler, and the heat transfer from 2 to 3 in a reheater. So putting them values, you can find the efficiency formula. That would be somewhere like this. So efficiency would be equal to the first stage work plus the second stage work minus the pump work, divided by the heat transfer in a boiler plus heat transfer in a reheater. Putting all these values, you can find the efficiency, which is equal to 40.3%. Uh, Now you can imagine like whatever the formula we were using, like that was the work done, or the work done formula, or the enthalpy Q in formula, that was per unit mass anyway. It because the enthalpy over here is specific enthalpy rather than the total enthalpy. So even the cycle efficiency was in per unit mass anyway. The cycle work done was per unit mass. So you have got the cycle work done now, which is the turbine work minus the pump work over here. It's written. Uh, then divided by per unit mass would be equal to this formula, which is over here. Uh, just putting them value, you can find the value of mass flow rate of the steam, which is actually required. Q out would be the mass flow rate multiplied by the heat transfer from 4 to 5. That's what actually the question was asking. I hope you understand the question. If you have got any problem regarding this question, you can post it in a Google Classroom, and I would be able to answer that one. One thing like it's a like finding the effect of reheat. Please make sure like you compare this example with example 8.1, and you would find out like by using reheat cycle, we have improved the efficiency, thermal efficiency of the Rankine cycle. Thank you very much. Have a nice day.